What is a 19-year tidal epoch? Let's read. Hey, Neil with US Captain's Training again. Let's talk about charts. We're going to start with the basics. The Mercator projection. That's what you're going to see on most nautical charts that you use. And what happens is this picture here from NOAA is really cool. It shows the globe surrounded by a cylinder, and all of the parallels and meridians are projected onto that cylinder. And then imagine the cylinder is rolled out flat. So when you take that globe and you open it up like an orange, all of those peels, they go onto that cylinder, but you can imagine they need to spread out to remain parallel and geometrically correct and meet at 90 degrees or perpendicular to each other. So this is the effect that shows that you'll see Greenland on a chart or on a map. Greenland looks the size of Africa. Well, it's not. Africa is 14 times larger than Greenland. But because of the Mercator projection, the very top of Greenland is very far north. So all those slices, they need to come together and even out. So when you put the globe in that cylinder, project the lines up the cylinder, lay it out, all the north and south get really big. Another good example of this is that strip on Antarctica. See how it's all the way across the bottom? That's because it's all the way around the bottom of the planet. It's not that it's huge or the largest continent. It is just that it is stretched out because of the Mercator projection. Here's another quick image that just shows you these little dots. See those dots? They get bigger as you go north and south. And again, look at the size of Greenland compared to the US, compared to Africa. The US and Africa are decently close to the equator, while Greenland is way north. So the top of Greenland especially appears gigantic. Despite this, we still use the Mercator projection because you can plot across the ocean even from point A to point B, and it looks like a straight line. Whereas if you did it on the globe, it would be this like compound curve. It'd be three-dimensional because it's on a globe. But in a Mercator projection, it just looks like a straight line. So we use that Mercator projection basically on all nautical charts, including the Block Island chart that we use to solve the problems in this course. Latitude and longitude. You can see this image here. Shows you latitude is like a ladder up the side of the chart, and longitude is east and west on the top and bottom of the chart. We only use the latitude to measure distances for these problems. I'm going to show you why. It's because 1 minute of latitude is equal to 1 nautical mile, conveniently. So people ask me, wait, how fast is a knot? Well, a knot is 1.15 miles per hour. So it's about every 8 knots you gain an extra mile an hour. So you're going 8 knots, you're going 9 miles an hour, approximately. But let's break this down. Why? Like, what is going on here? We can prove this. We can say there's 21,600 nautical miles per 1 Earth circumference, right? And if we put Earth's circumference on the top and 1 Earth's circumference, there's 360 degrees, okay? And then we put degrees on the top. So degrees, minutes. So in 1 degree, there's 60 minutes, okay? And now what do we get? So we should get Earth's circumference cancels, degrees cancel, and we're left with nautical miles over minutes. What does that look like if we put it in our calculator? I'm going to come show you. We got 21,600 nautical miles in 1 Earth circumference. 21,600 nautical miles in 1 Earth circumference divided by 360 degrees in 1 Earth circumference equals 60. So now we have 60 minutes per, okay, so divide that by 60 and we get 1. Crazy, right? So we got 21,600 nautical miles per 1 Earth circumference, right? In 1 Earth circumference, there's 360 degrees, and in 1 degree, there's 60 minutes. So we end up canceling these, and we get nautical miles per minute, and we end up with 1 nautical mile per 1 minute of latitude. Cool, that's why that works. All of that is to say that when we measure distances on a chart, we only use the latitude scale. Let me bring you in for a closer look of latitude and longitude. Okay, here's latitude, like a ladder going up the page. Here's longitude. And you'll notice that, you can use the scale over here. Where is it? Here it is. It'll show you nautical miles, yards. You can use this scale, but it's much less convenient than using a latitude scale. There's a couple other things I want to show you on this chart. Here's the compass rose. This star points to geographically true north. This outer ring is true. This is the ring that we use on all the problems. This inner ring shows magnetic. So this is where you are in the planet will change your variation. This inner ring accounts for variation. Let's come in even closer. Variation, 14 degrees, 15 minutes west in 1989. It's got an annual increase of 3 degrees. Okay, let's cover our bases. The outer ring of the compass rose on a nautical chart provides true directions. True north is at 0 degrees and is marked with a star. The inner ring of a compass rose on a nautical chart provides magnetic directions, which takes into account the variation of the location of the compass rose on the chart. Near the center of the compass rose on a nautical chart, both the variation and annual rate of change are indicated, right? Variation, annual rate of change. So you could actually calculate, this was 1989, annual increase of 3 minutes. Okay, this is interesting. So this compass rose is located over here, right, near Block Island, and it is 1445. Look at this. This one is located just, like, how many miles is that? 5, 10, 15, 20. It's like 20, 25 miles or something. So look at this, though. Variation, 1430. Annual increase of 4. What? 1430 over here. 1445 over here. Annual increase, 3 over here. And 4 over here. Interesting, huh? One more thing to note. Visible range used on charts. The visible range used on a chart is referred to as nominal range. Nominal range can be defined as the maximum distance at which a light may be seen in clear weather with a visibility of 10. The nominal range in nautical miles appears in the light list for all federal lighted aids to navigation except range lights and directional lights. In addition to appearing in the light list for all federal lighted aids, nominal range can be corrected for all conditions of visibility to get a luminous range. We'll take a look in depth at finding luminous ranges later in this section. Okay, so visibility used on charts. Let's find an example of this. Here's one. Watch Hill Point. Calting 61 feet. See that 15M? You can see this from 15 miles away when there's a visibility of 10. That's a nominal range. Let's go down here. Montauk Point light flashes every 5 seconds. It's 168 feet tall. You could see it from 24 miles on a day with a visibility of 10. So a nominal range of 24 miles. It's got a horn. Cool. The scales of these charts are going to range from somewhere between 1 to 14 million all the way down to 1 to 2,500 or so. So 1 to 14 million, this is a small scale chart, which covers a very large area. 1 to 2,500 is a large scale chart, which covers a small area. So small scale, large area, like a sailing chart that covers an entire ocean. And then you have a large scale chart, which covers a small area, like the inset on a chart, which covers only the harbor in great detail. So large scale, small area, small scale, large area. And there are different types of charts based on this. Let's check this out. Below is a list of chart types in order from smallest scale to largest. Sailing chart scales less than 1 to 600,000. A general chart, the scale is between 1 to 150,000 to 1 to 600,000. Coastal chart scale is 1 to 50,000 to 1 to 150,000. Harbor chart scale is larger than 1 to 50,000. So we're on a coastal chart in Block Island. It's 1 to 80,000. It fits right in there. Let me read you the definitions of these charts. These words are important. Sailing charts. Sailing charts are the smallest scale charts used for planning, fixing position at sea, and for plotting the dead reckoning while proceeding on a long voyage. The scale is generally smaller than 1 to 600,000. A general chart. General charts are intended for coastwise navigation outside of outlying reefs and shoals. The scales range from about 1 to 150,000 to 1 to 600,000. Coastal charts. Coastal charts are intended for inshore coastwise navigation, for entering or leaving bays and harbors of considerable width, and for navigating large inland waterways. The scale range from about 1 to 50,000 to 1 to 150,000. Harbor charts. Harbor charts are intended for navigation and anchorage in harbors and small waterways. The scale is generally larger than 1 to 150,000. So again, if you're wondering where Block Island chart fits into this, this is a coastal chart. It's intended for inshore coastwise navigation for entering or leaving bays and harbors of considerable width, right? That describes this Block Island Sound and Approaches chart very well. There's a couple more things about this chart that we should talk about. One is the datum. Chart datum is the reference level from which depths and tidal heights are measured on nautical charts. That's a definition right from NOAA. There's a datum for the depth, the sounding depths of charts that give mariners a little bit of wiggle room. That's called mean lower low water. So let me read it right out of here. Mean lower low water is the reference plane used for the depth soundings on charts of the U.S. East and West coast. Mean lower low water is defined as the average height of the lower of the two daily low tides observed at a specific location over a 19-year tidal epoch. They take all the tidal data for 19 years and average it. And then that's what this mean lower low water is. It's the average of the lower of the two low waters on a tidal day. And that is the sounding datum for this Block Island chart. And you can see it right. I'll just toss it up here. You see this? Right up here. It says Mercator Projection, scale 1 to 80,000 at latitude 41, North America datum 1983, World Geodetic System 1984. And now soundings in feet at mean lower low water. Let me just take you in for a closer look. Here we are. Here's the info on the chart. Mercator Projection, scale 1 to 80,000, and it gives the latitude from that scale, latitude 41. North American datum of 1983, World Geodetic System 1984. Soundings in feet at mean lower low water. So all these soundings on the chart, see that? And these contour lines, they go up 30 or down 30. You can see them 120, 150, 180. These contour lines, they're all based on the datum, soundings in feet at mean lower low water. Good. There's another datum, mean high water. This is the datum from which height measurements of hazards to navigation are taken. So a bridge clearance, for example, on the chart there's a bridge and you need to pass right through the middle of this bridge. It'll give the height of the bridge from mean high water. What does that mean? Why don't they use low water? Low water would give you a false sense of security, right? You say, oh yeah, I have enough room, but you only have enough room at low tide. So they say, okay, we'll take the average of the high tides and do that vertical clearance so you can be more sure that your ship's going to fit under that bridge. It makes sense, right? You take mean lower low water, which is the lower of two low tides, and do your depth. Now you have some wiggle room. And as far as clearances for your air draft, you get mean high water, which is the average of all the high waters. That makes sense too. A little bit of wiggle room, they'll give you the high water heights and the clearances above that water. So these, we have a chart datum. Let me read these right for you. One more time. Chart datum. Chart datum is the reference level from which water depths and tidal heights are measured on nautical charts. Depth sounding datum. Mean lower low water is the reference plane used for depth soundings on charts of the U.S. East and West Coast. Mean lower low water is defined as the average height of the lower of the two daily low tides observed at a specific location over a 19-year tidal epoch. Height reading datum. Mean high water is the reference plane used for the height readings of hazards to navigation on charts. For example, bridge heights are typically represented using mean high water as the reference point. Mean high water is defined as the average height of all the high tides recorded at a particular location over a 19-year tidal epoch. What is a 19-year tidal epoch? Let's read. Tidal epoch. The national tidal datum epoch is the specific 19-year period adopted by the National Oceanic and Atmospheric Administration, NOAA, as the official time segment over which tidal observations are taken and reduced to obtain mean values for tidal datums. So tidal epoch's just the time period from which they crunch the numbers to get the datums. That's going to wrap up our general chart section. We'll see you in the next one.